All right, so let's take a look at the section 7.1 homework here to talk through the solutions. Right, so we've got integral x e to the 7x. This is the classic form of a polynomial times cosine kx, sine kx, or e to the kx. Here we've got e to the 7x. So it's already giving you what u and dv need to be, but we know that in this situation in general, we set u equal to the polynomial because after computing du enough times, that polynomial term will become constant. And in this case, actually, after only one derivative, u turning into du, then du is just a constant. So yeah, so they've got here determine du and v. That's just taking the derivative of u using differential notation, and then to find v, we just integrate both sides. Remember that if e to the 7x has a derivative that involves a multiple of 7, the antiderivative of e to the 7x is going to involve a multiple of 1/7. Right, here, x times cosine 8x dx. This is very analogous to the previous example. It's essentially the same exact idea when you have a polynomial times cosine x sine x, or e to the x, or better said, I guess, sine kx, cosine kx, or e to the kx. Here we have cosine to the 8x. That's a perfectly fine situation to deal with. The antiderivative of cosine 8x is going to be what? 1/8 sine 8x. And yeah, use integration by parts, and life is good. We have a degree 1 polynomial, so we only have to use integration by parts once. Here, we've got ln inside our integral. So this is like A1 priority whenever it comes to integration by parts. If you see ln inside the integral, let ln be equal to your u, which means your dv is going to be t to the 7th dt. But that's fine because the derivative of u is not bad. That's just 1 over t, the derivative of ln t. And yeah, turning the dv into v is just integrating t to the 7th, which is 1/8 t to the 8th. Nothing too bad. This next example we actually went over in class today as a part of our Q&A. So this is the classic example that sort of loops around after two applications of integration by parts. You've got to use integration by parts twice, but once you use integration by parts twice, you'll get back this exact same integral in expression. Hopefully, I haven't actually done this. Hopefully they use u equals, oh gosh, they have u equals sine to the 4x. Well, we did it with u equal e to the 3 theta, but letting u equal sine to the 4x will still work. You'll just be taking the derivative of the sine and the antiderivative of the e to the 3x, but you'll see it'll work out very analogously. Maybe it was even better that we did it a slightly different way than the book here recommends, but it's really a personal choice in this particular example, whether you set u equal to your trig function or u equal to your exponential function. But I like u equal exponential, but whatever, that's just a personal choice. This next one, now here we've got an ln quantity squared. If we just let u equal ln x, that would make it difficult to write the entire integral in the form u dv, because if we just let ln x be equal to u, we'd have a u squared upstairs, and that's sort of a problem. So if we let u be equal to the entire numerator, everything involving the ln x, then that will help us out. And right, then as it shows here, the dv is everything else, which is the x cubed downstairs, or x to the minus 3 dx. And take it through integration by parts, and you'll get a nice result. Now, this one happens to have bounds of 5 and 1, but that's okay. Since we have bounds, all we're going to do is compute the antiderivative function and then plug in 5, plug in 1, and subtract. So that's not too bad. So we want to take the integral all the way. Once we take the integral all the way, we then evaluate the 5 and evaluate the 1. Here they're suggesting to use a capital U for the second substitution, because I think after the first substitution, you need to use a second substitution by virtue of the fact that we have ln to the x quantity squared. I think that quantity squared gives a second iteration of IBP as a necessity for this one, but so be it. Okay, here's another one where we've got bounds, but again, so be it with the bounds. It is what it is. In fact, they're suggesting to make a substitution first. So maybe we apply this substitution and then work from there. But yeah, ultimately, look, this is just going to take the form of a polynomial in front of cosine kx, sine kx, or e to the kx. Once you let x equal theta squared, now you just have cosine x, and that shouldn't be too bad to deal with. Right, tan inverse x. We did not do tan inverse x in class. We did sine inverse x in class. I'd actually recommend doing tan inverse x in class. The sine inverse x was, I mentioned it at the time. I said it'd be a great test question because when doing sine inverse, you not only had to use integration by parts once, but you also had to use u sub once. So it was actually kind of nice. Tan inverse x is completely in the same boat. You use integration by parts once, you use u sub once, and you'll resolve the integral. So I recommend that as an example to try. Frankly, I'll put it on our suggested exercises for the next test because it's a good one. So right, yeah, you definitely can use integration by parts on that. In fact, all the inverse trig functions derivatives can be found using integration by parts. And now this one, integral e x the fifth e to the x. Boy, this would be annoying to actually work out because that x the fifth, you're going to have to hit that nail with a hammer 5 times. But well, after 5 times, that x to the fifth becomes a constant, and then the integral would resolve itself. So yep, we do need to use integration by parts 5 times, but so be it. It is what it is. I think that's all the questions, and we'll move on to the next section.